All right, time for another draftphysics.com, debatephysics.com also. And, just keep trying to find somebody who will interact in some constructive way. So I have found a channel called Physics Problems and Solutions. I think I have responded to him in the past, but can't say for sure. Anyway, but maybe I'll answer the question. Does he really believe it takes 100 times the energy to spin a motor 10 times as fast? Does he really believe that's true? Because that's what their physics says. Yeah, that's the textbook definition of reality. So he deals with the ballistic pendulum here, which is kind of funny. And so I thought I would play this just because it's kind of funny. Because, yes, he kind of recognizes the problem, and he really doesn't have a solution. He just says it takes energy to move something, which really isn't Newton's third law. So I suppose that would be part of this conversation, is exactly what is Newton's third law, this equal and opposite reaction. Does something, hit something and, this goes this way and this goes this way, or does it hit something and stick to it and move it, or does it, how exactly is energy transferred? And I'd argue that the small universe is a little different than the big universe, but we certainly know in the big universe it just is a transfer. This has it. It can hit something that's the same, which I should be able to have right here. Yes, I do have. And we know it doesn't take any extra energy to move this. No extra energy. So his basic argument is going to be that somehow it takes extra energy to move something. When no, it doesn't. It just takes you have to just give it. So you can have $10 and you can give $10 to something else. That's all it takes. There's no resistance to it accepting the money. That would be the basic principle. So anyway, we'll play some of his video, and then we're going to do one on the relativity theory, the clock stuff, just because he has a video on the clock thing where they have sort of an interesting take on it, so it's worth conversation. But again, it's really easy to understand how they're just cheating the argument. So
I will try my best
okay.
answering.
Okay, that was the end of the video. Yeah, well, that didn't work.
Want to ace your class?
No, I don't want to do any of that. Stop it. Okay, I'll pause. Oh, this is the commercial from the math and science guy.
To practice while watching the video.
Yeah. So it is kind of funny. The commercial's a lot fancier than his videos are. But clearly he's paying out a lot of money for these commercials. And, he's still only getting a couple thousand views on his videos. And he's been doing it for a couple of years. I've been seeing these commercials for a couple of years. Anyway, well, a year anyway. Okay, so it took me 44-second commercial and it played twice. And, oh, what a pain in the ass. Anyway, so he said in previous video,
we discussed the projectile hitting a heavy object attached to a pendulum inelastically, and we found out that the energy is not conserved.
Right, no, yeah, the kinetic energy isn't conserved, so the momentum is 100%, well, could be, close to conserved, and yet the kinetic energy just disappears is the correct word. I mean, you can say it's not conserved, but the fact is it disappears. Okay.
The question that remains unanswered is, where is the remaining energy?
Yeah, where is it?
In this video, we are going to discuss this in more detail, and hopefully everything will make perfect sense.
Yeah, I'm going to speed it up. So it won't make any perfect sense. He's just going to say somehow it takes more than just your regular momentum to move the object. And we already know that, no, that's all it takes is your momentum. A bowling ball has a certain amount of momentum. It hits the pins fly off with a certain momentum, and you conserve the momentum. There's no extra energy involved. And so if we did it the opposite way, we have small things hitting a big thing, there's no extra energy required to move it. It's the same amount of momentum. So if we reverse the bowling ball hitting the bowling pins and we just reverse the film, it's still going to make perfectly good sense. The pins will hit the ball at a certain velocity. They'll give the ball the velocity. It's not going to be all that complicated. So again, just a mushy kind of answer, frankly. I mean, I like this guy. I like, I tend to as it's an accent that doesn't bother me as much. The Eastern European thing. But anyway, Russian.
Think about what exactly happens during the collision in inelastic scattering. In the moment of collision, the heavy object is going to apply a force on the projectile to slow it down. The same force is going to be applied by the projectile on the heavy object, and therefore it starts to move. And
Yes, and the whole point is there's so little force going in the wrong directions. That is, there's so little pushing in up directions and down directions and in directions that aren't conducive to conveying the motion, that you still end up with 98% of the momentum, let's say, conserved. So you still conserve a substantial portion of the momentum, and you lose all, essentially, of the kinetic energy. And frankly, the true scenario, I mean, he's doing a 10-to-1 difference. Obviously, a 10-to-1 ballistic pendulum wouldn't work very well. You really have to have 1,000 or 2,000 or 10,000 to 1 ratio. And in those circumstances, you just start losing a higher and higher percentage. It goes from 99%, let's say, to 99.99% to 99.9999999%. So the heavier I make this pendulum, the bigger the ratio between the weight of the bullet and the weight of the pendulum, the higher the percentage of the kinetic energy lost, going to zero. From every single bit of it, just about, to 99% of it.
Eventually, the velocity of the projectile will match the velocity of the heavy object, so they become merged together.
So it won't, the little object will slow down, obviously, and what it's going to slow down to is a speed that's so substantially slower. Like I said, in the real case, it's going to lose 1,000 times of its velocity. So it's going to go from 1,000 miles an hour to 1 mile an hour, that kind of ratio. So it's almost irrelevant that it's still moving. That's not really the point. The point is the big thing has absorbed the 999 miles per hour and absorbed it as a much slower velocity because it's a much larger object. But all of the momentum is conserved.
The important lesson to take from this is...
Now, the important lesson to take is why do we have two formulas for energy? Well, momentum was Newton's formula and it worked. It was Descartes and it was Galileo, and there's no point in insulting them by saying they didn't understand collisions when, frankly, they spent a lot of time banging pendulums into pendulums. You could even say Huygens. Huygens proved this. A lot of people who were wave people, who were relativity people, conceded these arguments, okay? I mean, Newton cites Huygens when Newton talks about conservation in collisions with pendulums, because Huygens did a lot of experiments. Huygens built clocks. He knew what pendulums did.
That the heavy object had to produce a work to slow down the projectile.
So it has to do work. It doesn't do work, it transfers its energy. So again, to say it has to do work, that means every single time there's a transfer, you're going to call that work. Well, frankly, all it's going to do is transfer the energy from it with one atom is going to transfer the energy to 1,000 atoms. No big surprise, the 1,000 atoms move 1,000 times slower. Makes perfectly good sense. Momentum works just fine. Kinetic energy is a nonsense.
But it didn't stop it completely because the whole thing started to move due to the impact. What we are interested here is the ratio between the final velocity and the initial velocity, because this is going to tell you what fraction of the kinetic energy of the projectile was transformed into a kinetic energy of the whole object.
Well, again, you can't, the velocities are going to be irrelevant unless you're going to multiply them by the masses. So clearly you're taking a tiny velocity for the ballistic pendulum over a ton of atoms, and you're doing the opposite with the bullet. You had very few atoms and you have a very high velocity. And obviously those two ratios are going to be the same when you finish. Instead of having one atom moving very fast, you're going to have 1,000 atoms moving very slow. Perfectly consistent, perfectly rational.
And what fraction?
Perfectly consistent with Newton's third law. The energy is just being exchanged. The bullet had $10. It's now given $9.99, okay, to the ballistic pendulum, and it's kept 1 penny. It still has 1 penny of velocity, okay? That's all it's got. But it gave away $9.99 worth of velocity to the to the bigger object, and the bigger object has lots of people to feed, so it split it into pennies and gave pennies to all the different little atoms.
Was consumed to slow down the projectile. If we compare these two scenarios, it is obvious that the bigger projectile is going to lose less velocity compared to smaller projectile.
It has to start with more. If the two pendulums are the same size, then yes, the bigger object is going the same velocity obviously has more momentum. So it'll give the pendulum more momentum. So that's kind of almost ridiculously obvious. Start with more energy, you will finish with more energy. More momentum. Momentum.
Projectile. And therefore, the ratio between final and initial velocity is going to be bigger. This should mean that in a second example, more energy was distributed into the kinetic energy of the whole object. Let's conduct some calculations to see this better.
Yeah, these aren't much, frankly.
Denote the initial velocity vi, which is, let's say, 100 meters per second, with the mass of the projectile m, and the mass of the big object 9 times bigger.
So 9 times bigger, again, silly ratio. And we know that, in the real case, it's 1,000 times bigger. A real ballistic pendulum. Much, much bigger. Much more massive.
But the whole object has the mass of 10m now, and we need to find the velocity after the impact, which we calculate from the conservation of momentum. We can move.
So you don't need to calculate, you can measure it, and that's usually how it's done, is it's measured. You measure its velocity, and therefore you can calculate then, okay, how much of the momentum has been conserved, or you can calculate the speed of the bullet, which is usually the part that you're trying to calculate because that's the harder one to know.
The mass on the other side and cross m, from which we get that final velocity is 10 times smaller than the initial velocity of the projectile.
So perfectly consistent, and in the real case it'll be 1,000 times slower.
We see that there is a significant decreasement in the projectile velocity, so the big object had to put a lot of work to slow it down.
Alright, so again, a lot of work to slow it down. No, all it did was transfer the energy from one object to the other object. The momentum didn't do any work. The work is still there. The energy is still there. It's still going in the right direction. You usually call something work when, a loss like friction does work against the motion because it takes it and it makes it kind of disappear. Work usually uses something up in the sense that it isn't apparent where the energy went, but obviously just transferring, that's all that happened. You just transferred it. You took it from one small object and gave it to a really big object.
And only a fraction of the initial energy is left for the movement.
So only a fraction of the initial energy is left for the movement. So again, what sense does that make? We perfectly conserve the momentum. It makes perfectly good sense. And because of your silly math, okay, you're saying there's some other energy that somehow disappeared or did something, did some work. Well, you're not going to be able to prove it did any work. You're not going to show me that there's a bunch of heat coming off of here that's going to equal, let's just use a joule number. Let's say you have 2,000 watts, going in, and you only have 2 watts coming out. Okay. So that's what the momentum converts into. In this case, we're going to convert the momentum into the kinetic energy equivalent. So you have 2,000 going in, you only have 2 coming out. Well, you have to prove that there's 1,900 worth of energy, okay, that somehow is dissipating as heat, or you can show that the clay has been deformed with that much energy. But you can't do any of that, okay? There's no experiments that measure any of that, so that's just a story. That's just made up.
From our calculations, we expect that only 1/10 of the initial energy was transformed into movement.
So only 1/10 was transformed into movement when we know exactly the opposite is true, that almost all of the energy was transformed into the velocity of 1,000 pieces. 1,000 bits of matter are now moving 1,000 times slower. It's all still there. It's a lot of stuff it moved.
And the rest was used for slowing down the projectile.
So that didn't, whatever that means. There's no slowing down the projectile. This doesn't use any energy to slow this down. This gets all of the energy. So let's, how can he make up this story? How come in this case, nothing, we don't lose anything to slowing anything down. We slow this down to 0. It doesn't even go any velocity. It crashes in and goes 0 velocity. So it doesn't have anything left. So we didn't just slow it down, we stopped it. And yet somehow we've perfectly conserved everything. Everything is perfectly conserved. So how can in one case you get perfect conversation, yes, of the momentum and the energy, and in the other case somehow the energy is who knows? So I just changed the mass that I'm hitting, and somehow I'm going to lose all the energy. And if I make it smaller, I gain energy. I make it bigger, I lose the energy. Come on, obviously a gigantic paradoxical flaw in the theory. Can't be true.
You can easily check if this is true by just calculating the kinetic energy of the...
So what you ought to do is take a thermometer or some other device and actually show us the 2,000 joules somewhere. Show us the bullet making them. Show us the pendulum making them. Show us somewhere that these joule numbers make any sense at all. Show me the bullet coming out of the gun doing 2,000 times the work that the recoiling gun can do. And then explain to me how it's consistent with Newton's third law, where obviously these won't be equal and opposite reactions. The gun fires and all of a sudden I got 2 joules going that way, and I got 2 watts going that way, and I got 2,000 watts going that way. Obviously not equal and opposite reactions.
The projectile and the whole object after the impact separately. The initial energy is the kinetic energy of the projectile, and the final energy is the kinetic energy of the whole object moving with the velocity vf.
Right, and you lost, as Professor Lewin states, in a real case, 99.94% of the kinetic energy is missing. And you can't account for it. There's no, you can just make up a story. Well, there's 2,000 joules worth of energy going someplace else. Show me.
We know that the final velocity of the whole object is 1/10 of the initial velocity, so we can plug that in, and by some simple algebra, we get this equation. We see here that this is the expression for initial kinetic.
So the problem with this, what he's doing here is the square term, he's not applying the square term to this velocity number, and so, you know, the ratio is still going to be gigantic, not 1/10. You're not going to lose 1/10 of the kinetic energy, you're going to lose 1/100th of it.
Energy of the projectile. So the final equation looks like this. So we see that the final energy of the whole object is 10 times smaller than the initial kinetic energy of...
Okay, so this isn't true. It's not 10 times smaller. It's 100 times smaller, and it would be 1,000. If you did a real case, it'd be 1,000 times smaller. And in the real case, it's, you know, like I said, it's, you might as well say it's 1,000,000 times smaller. 99.94 is probably, you know, getting close to 1 in a million.
The projectile. So that's it for this video. If you have...
All right, so absolutely no explanation here. So he did 2 videos. First, he does the elastic collision thing experiment. No, he doesn't do it. He just illustrates it, of course, and points out the paradox. And then he does this as a solution, sort of, and it solves nothing. It doesn't explain at all where the energy went. Where did 99.494% of the kinetic energy disappear to? Where's it going right now? Where in this drawing is it dissipating from this closed system? This is a closed system. You have to explain where the hell it is. You had it and now it's gone. Where is it? So really bad, frankly. All right, so we'll move on to the relativity argument, but really just a really poor, again, 10-ton train, 5-ton train. So I can just take the 5 mass going, you know, let's just draw it just for the sake of, let's just show that this happens wherever they go. This is what the formula does. It messes up everything, every single circumstance where you have an increase in the velocity, it just makes an absolute mess. I mean, you have an increase in the, you change the mass. So, you know, the simple scenario, right? This will work, right? Yeah. Okay, I have the 5 mass going 10V. I add 5 mass. I end up with a 10. Okay, mass going 5. Everything looks just fine. Newton's happy, Descartes happy, Galileo's happy, everybody's happy. They show up with their 1/2 mv squared nonsense, and they tell us that this has, let's say, 100 joules, and this only has 50. So somehow I lost half the kinetic energy is gone. 1/2 the kinetic energy is gone. It's missing. But I have 99.99% of the momentum has been conserved. So I have all of the momentum, and yet somehow I'm supposed to believe I made things fly off, or I did something that recreates motion. So I gave motion to other objects, but I didn't use any momentum to do it. When, yes, we know that in this universe, if the bowling ball hits a pin, it has to lose its momentum for the pin to have it. The pin leaves with what the bowling ball lost. That's how exchanges work. You don't get to exchange it and keep it. You can't exchange it and keep it. You can't give away $5 to somebody without being $5 poorer. There's no way to give them $5 and keep your $5. I mean, come on. This is minor logic. It is grammar school logic, frankly. And we just keep playing this game. In spite of the fact that you can point out how this is Leibniz's physics. He believed that dropping 4 pounds from 1 foot was the same as dropping 1 pound from 4 feet, which it obviously isn't. And then nobody believed it. Leibniz died a nobody, essentially, in disrepute. Resurrected in the 1700s with silly clay experiments that are illogical, denting clay with round things, hitting sand with objects that are going fast and slow, and then only measuring how far a piece of sand goes. I mean, totally illogical crap. And, I can sit here for 3 years pointing out how it's all crap, and they'll never do me the courtesy of providing the counter argument. That somehow it's not crap physics has never been proven. They've never shown it taking 4 times the energy to spin a motor twice as fast. They'll never show it taking 9 times the energy to spin a motor 3 times as fast. They're never going to show it taking 16 times the energy to spin a motor 4 times as fast, and on and on and on. They're never going to show it because it doesn't actually happen, because their physics doesn't have anything to do with reality. All right, back for the light clock. Okay, Einstein time dilation kind of argument.
About the electrodynamics of moving bodies. This paper solved a critical problem of its time, the clash between Newton's laws of motion and Maxwell's electromagnetism. However, to achieve this success, Einstein had to sacrifice.
So there really isn't any success, and the Faraday paradoxy thing still sort of exists. They still have a misunderstanding of the nature of the creation of the magnetic effect caused by electricity, which I would argue is just a symptom of passing electricity through a wire. So every time you distort atoms by electrifying them, they will become polarized and create a magnetic effect. And the fact that you have to use high amperages and low voltages just explains the fact that you have to involve more atoms, and it's just the way the conductor ends up looking. It's not producing any more force, it's just reflecting the universe differently. So you could just say when you pass electricity through a wire, the color of the wire changes. You could just say that physically changes its appearance, and so now it reflects the light different. Now it's a mirror instead of being opaque. You could make that kind of argument. It goes from being absorbing energy, let's say, to reflecting all the energy.
As a law, since some quantities that were thought to be absolute for decades become relative, and were replaced by different quantities that are much more abstract and harder to imagine. And
right, so it's all a shot against everything that Maxwell was built on, which was Newton, Descartes, and Galileo. So let's just throw all that science out and pretend time isn't a function, and let's make it into some sort of silly dimension.
Because of this rearrangement of the relative and absolute quantities, we call it a special theory of relativity instead of just relativity.
Well, I think it was called special because it was about the special circumstance of acceleration, but whatever.
So if somebody tells you that Einstein teaches us that everything is relative, he's lying to you. It is just that the relative and absolute quantities are different than you originally thought.
Okay, so there's nothing relative but our perspective, and our perspective is controlled by how long it takes light to get to us, so it has absolutely nothing to do with anything. And nothing in the physical universe is actually at all affected by any of this relativity crap, and it just has to do with when we see something. Well, when we see it isn't when it happened. So it's that obvious. To blow the whole thing up, you just say, hey, Okay, think there are simultaneous events. Two events happen simultaneously. The fact that you're closer to one and see it happen sooner doesn't mean this one happened later. So it's just idiotic to think so. So frankly, what's the point? So I'm traveling 99% the speed of light. If there was a window, I look out the window and I see the rest of the universe getting a beard and dying of old age. And it's not somehow apparent to me that all I'm doing is being frozen, that I'm cryogenically changing. But I am not in any way. Time hasn't changed. The time is still ticking everywhere the same. All right. It's just that somehow my metabolism has changed by magic.
The important quantity that had to be sacrificed is time. And whenever a new person learns
So silly. So the most reliable thing you could almost say in the universe, time. I mean, Old Faithful. I mean, all that. It's just. Let's just play games that somehow I throw something over there and it's in some sort of different time frame. No, it isn't. There's this time right now. You could go 1 billion light years away and it's exactly the same time there. But the point is, it takes 1 billion years for you to know it's the same time over there. It takes 1 billion years to see the clock. There's no whatever this nonsense is.
about special relativity, this is probably the first thing they learn. Time is relative. This means that whenever you see clock moving, it will always tick slower than yours.
All right, so again, it doesn't even make any sense. You can't see moving clocks, blah, 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 blah. Can't see them ticking, and none of that happens. So, yeah, let's just make up stories about what clocks do. Ugh.
And from this, you get all the fun stuff, like twin paradox and so on. But whenever you attend a
Yeah, and all nonsense stuff,
special relativity course, you will always learn about the time dilation the same way. And it is by using light clock that bounces.
All right, so it doesn't make any sense. So this whole description of a light clock is just nonsense. So what they're assuming about photons doesn't make any sense, right? Einstein himself is the one who basically said, look, it's like quanta. It's a clump of quanta. And the quanta moves in a straight line. The quanta is not a wave, okay? The quanta isn't going in all directions at the same time and then deciding to be in one place. Einstein was opposing that gibberish, that spooky action kind of crap. So the whole point is the light clock, a photon can only have one direction. A photon can't be going this way and this way at the same time. Can't go two directions at the same time. Not possible. It can only go one direction.
A photon off of a mirror, and every time this photon makes a round trip, we detect it on the detector. And by this way, we define a unit of time. Special relativity is based on a postulate that says that the speed of light is independent of the motion of the source.
So, yeah, and that's a perfectly rational thing to say. So it doesn't matter how fast the thing that's going is. Relative to absolute space, the photon's going to go the speed of light. So relative to something not moving, it's always going to pop out. It can't pop out with extra speed. I can't go 50 miles an hour and then add to the photon 50 miles an hour and make it go, 3 million blah, 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 and 50 miles an hour. I can't make the photon go faster. I can't push it faster. It's always released at the same speed. And their own theory is saying that that's true in the sense that the only way you could perceive a photon leaving, so say I'm going half the speed of light, the only way I can perceive the photon is going away from me at the speed of light, because obviously I'm going half the speed, it's only going 1 unit of speed, I'm going a half unit of speed, therefore it can't leave me at a full unit of speed, right? It's only going to be leaving me at a half unit of speed per time. And the only way I can see it as leaving at the speed of light is if you cryogenically break me, and if you make me not be me anymore, and I'm some sort of slowed down thing, okay, and I'm not seeing reality. And that's the truth. I won't be seeing reality because we know the rest of the universe is still going the real speed. And if I could look out the window, I could see that I'm going half the speed that the rest of the universe is going. So again, they're conceding the point that the photon actually leaves at less than that speed in actual space. It actually leaves only half the speed of light away from me if I'm going the speed of light. And it gets worse and worse. So the closer I'm going to the speed of light, I turn on the flashlight. Now they say I'm asleep for 1 billion years. You know, my system is slowed down, so 1 minute for me is 1 billion years for the rest of the universe. Come on, nonsense.
It's always one number.
Okay, so they draw this without doing the line thing. But obviously, that's not what a photon does. You can't give a photon motion this way and then give it motion this way. You can't make a photon move with the ship. So I'll draw it, but I mean, come on. I shouldn't even have to do this. I mean, clearly, okay, you can't. Photons are emitted. They pop out of whatever they pop out of at the speed of light relative to a dead universe, a spot that isn't moving. All right, it's always that case. They always move the same speed. So if you actually had an actual rocket ship, okay, and you're going to do this stupid light clock crap, well, let me make it much bigger because, frankly, yeah, frankly, the camera isn't even all that good. All right. All right, now I'm going to put a light clock in my spaceship, right? Okay, so, all right, look, the point is the side of the ship is moving, okay? When I emit the photon isn't going to be, the photon is just going to go in one direction, the direction I emit it in. If I emit it this way, then it's going to go across this direction. If I emit it this way, then yeah, it's a different direction, a different distance. But I'm emitting it straight across. The ship moves. So the mirror's now gone. I can't reflect off the mirror. If the mirror's here, I can't reflect off of it anymore. Now, if I make this whole surface a mirror, then the light clock can still work to some extent because it's going to go straight across. The mirror moves, okay, and it comes back, and it's going to keep perfect time. It's not going to be slowed down then. It's going to go across and back, and it'll be perfect. So as long as I make the whole side of the ship mirror, and I have a very long ship, no problem. The light clock does what it's supposed to do. But this idea that somehow the photon is going the speed of light this way and the speed of the spaceship this way, no, it isn't doing this at all. Okay, photons cannot go two different velocities. They can only go, they only have one vector. They only go one place. It's a straight line force universe, okay? Things don't do this. I will move this way and I will drift this way. It doesn't drift. Photons don't drift, so none of this crap happens. It's totally unrealistic nonsense. So here they are. You know, you can't do this actual experiment, but they should at least get it right. And the interesting thing is the guy does it with sound, and sound kind of just proves the point that the sound waves they will be receiving aren't going to be the ones going straight across. They're going to be receiving ones that are going the diagonal. I mean, it's just, you know, it's so easy to figure out the gimmick.
This clock is moving or not. And because of this, in the moving clock case, the light has to travel a longer distance than in a stationary case.
And if it was, let's even say it was traveling that longer distance. Let's say it could actually do this drifting thing. The fact is it would arrive at this other side, though, at exactly that same time. It would go the longer distance faster than the speed of light, because you can't change the fact that it's doing this way at a constant speed. So it's not going to slow down this way because it's drifting this way. So you can understand that the drift going up can't change the speed going this way. So it's still going to arrive at that point further up, okay, at exactly the same time if it would have been a straight line. So it's not going to tick any slower because you can't change this speed of light for this distance, and it's going to keep going this way as it's being drifted this way. So even if they did this honestly, the fact is this clock would tick exactly the same as the other clock because the distance the light is traveling at the speed of light is the same. The fact that its actual distance ends up being further because you gave it two velocities, that's not going to change the fact that it did this at the speed of light and it did this motion at the drift velocity of the spaceship. And it did those two things within those times, meaning it's going to hit this surface at exactly the same time as the straight line.
And therefore, the number of time units passed on each clock will be different. If you did the math, you would end up with the famous time dilation equation.
Yeah, which is a pile of nothing. It's just gamma. This whole section here is just some, let's fix it so it doesn't run into infinities. So that's all this is for. And you could write this equation the same way by just pointing out that if you're trying to push something in the real world, as you're pushing it, it never gets technically lighter in the sense that it's never going to weigh zero. So every time you're pushing it, even if you're adding more and more and more and more force, it still weighs more than nothing. It always weighs something. You can only do it by percentages. You can take you can convert your velocity into a percentage of velocity in a bigger thing, but you can never give the bigger thing more velocity than you have.
Which tells you how longer the period on the moving clock is compared to a stationary one. And from this, we say that time runs slower for a moving observer.
So you say it, and it's just completely theoretical mush. It's not very realistic. What's the argument can be made? It's just an insult to the whole Occam's razor thing. You're picking the really weird thing to say is the thing that's messed up in the universe. And on top of that, it's not even logically consistent. The light clock won't work the way you drew it.
Natural question is, what happens if you change the clock and make two mechanical clocks move relative to each other? Will the moving clock tick slower than stationary one? How can we know that time dilation is not just a clock issue? Because if it...
Well, we know it's just a clock issue. Frankly, I just don't know how you can't know it's just a clock issue. All clocks are breakable, and even an atomic clock is breakable. Again, I put uranium atoms closer to each other, and I change their half-life. I change their rate of decay. So obviously I can screw up any clock.
Applied only to a specific clock, then...
Did you know that every time you check your email, an e-farmer makes money? There are people out there that are called e-farmers.
Then our biological age would not change in the twin paradox scenario. So all the fun stuff will become boring.
Right, so I mean the very idea that they just make up this story that somehow by moving you have some kind of atomic clock in you that's going to be affected when there's no evidence you have atomic clocks inside of you. You're not that same kind of clock. And there's clearly no evidence that they've shown that sand dials don't, that change, or that some other clock measuring time is going to be broken by this effect.
You might say that time dilation was experimentally proven by a number of experiments.
So you might say it, and you're just doing the same thing physics always does. Oh, we've proven that light's a wave with the double slit experiment. That's really the single slit experiment because you have the slits so close to each other, the 2 point sources are so close that you can't get a difference, a wavelength of difference from those two sources. And it's really just the surfaces experiments. It's a 2-source experiment, the 4-source experiment. Yeah, it's just sources. So yeah, you do everything. You jump to these wrong conclusions. You make this, you establish this as a fact. You have a diagram of the atom that says the electrons are swirling around at 473,000 miles an hour. Well, what's your evidence for that? I mean, when the simple argument is you know that atoms share an electron. Now, how does it make any sense if that electron's moving 470,000 miles an hour that you can in any way be sharing that electron? It seems to make a hell of a lot more sense that the electron must be in a pretty stable condition and the two atoms are physically sharing it. But no, you won't fix that diagram either. You got plus and minus wrong and you never fixed it.
And we didn't use this light clock but atomic clock. And also GPS satellites need to use this time dilation to keep their atomic clock synchronized with the ones on...
Right, so he's not even going to point out that, guess what? Well, guess which one's broken? The one on Earth is the clock, okay, that's broken. It's moving way too slow. So that's the irony, right? Somehow the people on Earth are moving too fast. They're the ones going too fast. They're the ones with the extra velocity. Right, because they are actually the ones doing the light clock thing. They are moving two directions at the same time. You're going up and down in gravity, and then you're being swirled around on the surface of the Earth. So you are doing a lot of this, okay, which is a lot longer distance. So it's like the basketball player and the ball. The ball is traveling a lot more velocity than the person running down the court. because the ball is going up and down while it's going this way. So it's traveling a longer distance in the same time, which means it's going a higher average velocity. So the people on Earth have the high velocity, the satellite has the slow velocity.
Earth, making them accurate. But what are these atomic clocks anyway? Isn't it just a hidden light clock? Since it counts the number of...
So it's really not. I don't know how you know what it is, okay, in terms of what's causing the energy to accelerate or decelerate a physical process. So clearly this little drawing doesn't have anything to do with any kind of real mechanics of an atom.
Oscillations of an electromagnetic radiation that is produced by some standardized atomic transition. To answer this question, I want to briefly mention a video from the channel Dialect, as they were able to reconstruct the time dilation using sound waves.
So I love that. I mean, I don't know how I missed that video, so I really have to find that. So they made a sound clock, right? But the trick with sound is, I'll draw it, okay, just to make sure it's well understood. So we get rid of this for now. And because it really is clever, but it's it just points out how it's a huge cheat. Sound cheats, okay? Sound can do something light can't do. All right. So, and especially by Einstein's own reasoning, and this is the disappointing part. I mean, it's that it's Einstein who's arguing in a lot of respects that the focus on waves is excessive, okay, and that particle physics should have more particles in it. So yeah, they built a light clock, okay, so it's a clock they can move. It's the same idea. We're going to move energy from here, one side to the other side. But you can sort of understand that a sound wave doesn't go this way. It's not a laser beam, okay? It's not going up and down. It's going in all directions. So what's going to happen is now when they move this whole thing this way, you can understand that the sound they're going to hear over here, right, on the receiving end, is going to hear, it's not going to hear this sound wave. This sound wave is going to shoot up, and this is going to be gone, and it's going to keep going this way. The sound wave they're going to hear is the one when going this way. The energy going, the molecules going this way are the ones going to be received here. So they are in fact going to travel this much longer distance. So it's going to take them longer to get to the speaker because they're traveling a much longer distance. So obviously this clock will tick a lot slower. And it's because it's not a laser beam, right? We know a light clock we can make with a laser beam. There ain't going to be no light going this way. There's going to be light going straight this way. That's it. Okay, and there's some dopey argument somehow it could possibly drift, but I'm telling you, light can't go two directions. Light can't go the speed of light this way and the speed of light that way. No, photons can't do that. All right, that's probably enough of that. I mean, you sort of get the idea, right? The sound is, in fact, a wave in a medium. Okay, so it's atoms are moving in these different vectors from the source. So the sound is being produced at all of these vectors. So it's like having a light clock where I have a laser beam pointing in all the directions. And now I'm going to receive the laser beam that goes over this way. So I shot the laser beam deliberately in this direction, perpendicular. Okay, I shot it in that perpendicular direction. Yeah, I can use the board. I shot it in the perpendicular, so I have laser beams going in all these directions, and then I received the light from the laser beam I pointed in that wrong direction. Obviously, that laser beam will travel a longer distance, and it will be a slowed down light clock. But that's not what the light clock is supposed to be doing. The light clock is supposed to be shooting one laser back and forth. It's not supposed to be shooting lasers in all directions. So it's really an interesting catch on the experiment. It's, but again, it's just the obvious cheat is this thing, the sound clock isn't shooting sound in just one direction. It's shooting it in all the directions, and therefore it's just going to receive the sound wave that did travel the longer distance. Yeah, that's enough of that. Continuing.
Medium instead of light waves.
Now, when the clocks are reunited, you find that less time has elapsed on the traveling clock than on the stationary one.
And not only that, they even reconstructed the whole twin paradoxical scenario using such a clock.
Now we can repeat this.
So it's a big cheat, basically, to say that that's what actually is happening and it has anything to do with our metabolism, that somehow our metabolism is built on cheating, like somehow we have laser beams inside of us that are shooting in all directions. Pretty unrealistic mush.
Experiments assuming any arbitrary initial velocities of our sound clocks with respect to the air, and the end result will always be the same. Whichever clock turns around to rejoin its companion will always end up showing less elapsed time. This is in consequence of it achieving a greater total average velocity with respect to the air over the duration of its trip. Likewise, in special relativity, we find that for any two clocks that are separated and rejoined, whichever clock turned around or accelerated to rejoin its companion will always end up recording less elapsed time.
Right, but this turnaround thing is another let because frankly, you can turn around something by slowing it down, or you can turn something around by merely using gravity. So let me just draw that real quick too. You really do have to illustrate points, I think. If you're not going to be bothered, if you're going to be bothered doing this kind of stuff, you really do have to illustrate the point. So the key thing with accelerating, that is, you're going to go somewhere, all right, and then you're going to come back. The idea is you have to do all this decelerating, stop, okay, all right, and then start up again and do the whole accelerating process. So you're doing the accelerating process twice. First you're decelerating, then you're accelerating. So that's part of that equation. But if you just left going around gravitational objects, you can get all the way without ever changing your velocity. So you just use Neptune and Pluto and whatever, you just use planets to create a gravitational bend in your orbit, and you'll never have to slow down. So you'll never have to accelerate and decelerate. So that would be the interesting question, is whether the acceleration is the source of this change, okay, or whether it's just the fact that you're moving a velocity. You certainly would be able to tell the difference between those two experiments. All right. Continuing.
And this is no surprise, of course, since the derivation they use is exactly the same as is commonly done using light waves.
But if the clock is in motion, the distance that the sound...
So it's not the same as light, because obviously light isn't going to go in all directions. So again, it's just such a canard to imply that a laser beam shoots lights in all directions, because it doesn't.
The wave has to travel between detectors now becomes greater than d, meaning it takes a longer amount of time for the wave to travel that distance, and thus a longer time for the moving clock to tick.
But they were able to do all this while having a preferred frame of reference where the clocks are running the fastest, and namely the air itself. But what if we had a version of atomic clock that would be using sound waves instead of light waves? Well, in this case, you can...
So again, it doesn't make any difference, really. I mean, you're just, the drag of the medium is a minor effect. The fact of the matter is that you are just shooting something at a different location that's further away. And obviously it's going to take it longer to go further.
The number of oscillations in the created sound wave. But if the source was moving relative to the air, there will be a shift in wavelength of the sound. And since the wavelength is longer, it will take more time to make the same amount of oscillations than for the stationary case. And therefore the stationary clock would see the moving clock run slower. So the atomic clocks are basically light clocks. So we can't easily say that experiments measuring time dilation using atomic clocks...
So the velocity isn't going to be enough to change the wavelength by anywhere near enough to account for the difference in the distance. The distance is going to have a much greater effect than any frequency change. You can't blame a Doppler effect, because the Doppler effect is going to be tiny at these minor velocities.
...are really proof that time slows down in motion. So if there was a similar medium for light as there is air for sound, then using atomic clocks we wouldn't measure any difference from what we are measuring right now. Of course, sound waves are...
but how could you possibly turn a photon into something that is going, a laser beam shoots photons in one direction? What's your argument? How do I get the photon I shot this way to go that way?
Which has some limits. You could put one clock in a box to protect it from air, and it would show the fastest time, which you could use to determine the rest frame of the outside air. But if there was a similar medium for light, it must be such that it doesn't interact with matter. Otherwise, the Earth would slowly spiral down to the Sun due to drag, and therefore such a box for atomic clock.
Right, and the fact is, though, yes, there's no medium. It is the force is what it's dragging into. So the force is hitting the force, and the force can't lose any momentum. The force is frictionless, so it doesn't lose any momentum in interactions because there's no such thing as friction for the force. There's no thing that can stick to a force and steal its energy. So obviously it can't be dragged. Okay, but matter can be, and that's why electrons and protons don't fare very well.
Would not work. But there is another issue with the sound wave analogy. If you are passing by a clock that is at rest relative to the air, you would see it tick faster than yours. And theoretically, if there were many clocks, you could find the one that is the fastest, and you would know that it's stationary.
Right, duh. So, I mean, obviously, all the clocks that are moving are going to... the sound will not be the sound that went straight across. So in any clock that's moving, you're not going to see the straight across sound. You're going to be seeing the sound that went sideways, that went at some angle. So the faster it's going, the more of an angle there's going to be. So clearly, yes, the only clock that has to be the fastest is the one with the straightest line. And the only one with a straight line is one not moving, obviously.
Special relativity, every time you see a clock moving relative to you, they tick slower. The problem is that in real world there is nothing faster than light, and therefore the only way to check how fast a clock is running is to check. But if you are walking, you have to include a longitudinal Doppler effect.
Have you ever thought about
So again, I don't think the Doppler effect is going to be significant depending on what velocities you're comparing. I'll just try to skip this. All right, we're back.
Of the clock you observe will be faster if you are moving towards it, and slower if you are moving away from it, due to the fact that the wave has to travel different distance.
So that's more just crap about how we see things. And so, yes, of course, we're going to see it different. But we're saying that what if we electronically tie a wire to it so we hear the ticks through an electronic wire? Then we're not going to have to worry about any of that seeing crap.
To the observer after each tick. If you calculate the contribution from the longitudinal Doppler effect, you will get that for the approaching clock, the time interval on your clock is equal to the 1 minus beta factor, where this beta is the velocity in the units of the speed of light. If you are approaching, let's say, with a velocity of 0.86 c, then each second on the observed clock would be cool only for 0.14 seconds on your clock. So you would see the clock running fast, and even if you accounted for the time dilation of the clock, you will still get 0.28 seconds for each tick. So it is not true that in special relativity you must always see the moving clock running slow. So now I want to summarize.
Yeah, so you can cheat because of your perception again. So yeah, you can see all of the clock's lifetime very quickly by it moving towards you really fast. So if the clock moves towards you really fast, then you're going to see everything the clock did really fast. And if it's moving away from you, clearly you're going to see it over a longer period of time. So you can slow down how fast the data gets to you.
All of what I said so far. The sound wave analogy predicts exactly the same result for a twin paradox scenario as in special relativity. The sound wave analogy predicts that one observer could see other clock running slower than his own, but that is also the case in the special relativity due to longitudinal Doppler effect. The atomic clock is basically identical to the light clock, and since the medium for light doesn't interact with the matter, we can't use this trick isolating the clock from this medium to measure the real time speed. And ultimately all clocks we are using today are somehow using the electromagnetic interaction, so that the atoms can communicate with each other. And therefore, these interactions slow down in a moving frame.
So says you. All right. So I'd say they're mostly using atomic clocks, or what they call them, atomic clocks. They're actually using the decay of some isotope. And all you're really saying is that you can change the decay rate of an isotope by giving it velocity. That somehow that retards the decay. So the more velocity I can give a radioactive isotope, the longer it will, the higher its decay rate. It's,
So ultimately, it might be the case that every clock we are using today is some version of a light clock in the end. So what makes us believe that special relativity is somehow special after all? I want to apologize now because some of the stuff I said were quite misleading. And some of you might have already noticed and be quite angry with me. But I want all of you to pause and think. Is there anything that makes an ultimate cut between sound wave analogy and special relativity. Okay, so to make the cut, we have to ask a simple question. Is there a simple clock that deviates from the light clock depending on the velocity relative to this ether? And by simple, I mean we can calculate the elapsed time on this clock and compare it with the light clock. And it turns out it is very simple. All you need to do is to just turn your clock by 90 degrees.
It doesn't change, so he's implying that that's going to somehow fix some problem, and it really doesn't, because now the clock is just going to take longer to tick one tick, and then the second tick, back will be really short. So if you're not counting the distance, the time it takes to get back to the clicker, okay, back to the source, if you're not going to count that, then yeah, it matters. But if you have to wait for the signal to come back before you can send the next tick, then it's going to tick exactly the same speed, because frankly, yes, you're moving the back of the ship towards, and you're moving the front of the ship away. So yeah, it takes longer to get to the front of the ship, but it takes no time at all to get to the back of the ship. So the return trip is 1/1,000,000th as long a distance as the going trip, but it ends up being the same amount of distance in the end.
Because so far, all of our discussion was about clocks that move perpendicularly to this medium. And I've already told you that the longitudinal effects on the elapsed time has much greater impact than transverse effect.
Why is rowing with hydro
Pretty annoying. Yeah, I understand. The guy's a student, he's got to make money and all that crap, but alright, so I'll just draw this real quick. Just make my point, which he doesn't really illustrate. Okay, but clearly, should erase better. Alright. So the idea is that you're going to just do your light clock this way, and you got these two surfaces. This surface is moving away, this surface is moving towards, in a sense. It's going to be moving towards the reflection. So you emit the light, and what happens? Well, as it emits, obviously this is going to move. So this will be here instead. So it's going to take it longer to get to the surface that it's going to reflect off of. But obviously while it's doing that, this has also moved the same distance. And now as it's coming back, it's going to be even closer. So now the return trip is going to be a lot shorter. Okay, so yes, the going trip is going to be much longer, but the return trip is going to be much shorter. And obviously, because it's the same speed for the object, it's going to end up being the same distance in the end. So when you add up this line and this line, you're going to end up with the same length of line you had when you just went straight up and down, back and forth. So the clock will tick at the same rate. If you count the return trip. Yeah. All right. Put this back. Put this back.
Clock, the time dilation factor is like this, whereas for rotated clock, we get a different factor. So the time dilation would be way stronger on such clock. So in the sound analogy universe, if we had atomic clock and rotate it, its time would run differently.
So again, he's sort of changed these clocks. So he's done this animation. One animation you had to wait till the other one came back down. This animation just keeps shooting, and it's not waiting for anything to come back down. So it's sort of a cheat.
Therefore, you could easily conduct
You can see it there, right? It's not
an
returning.
experiment which would tell you how fast you are moving relative to the air. The GPS satellites would have to make sure that all clocks have the same orientation all the time. Otherwise, the accuracy would go through the window. But in our
So I don't know. He sort of had little tiny numbers there. Let's see if he has the right clocks going slow. Just I'll be a jackass about it. He has this clock running faster, the one on Earth. So he has it backwards. This is the slow clock. The one on the Earth is the one running too slow. The one out here is running too fast. So he has it backwards. Not that, that kind of crap is huge, but, frankly, it is sort of an interesting point to make, is that, because they'll argue about what theory fits here, and it's really the gravitational theory. The gravity is what's causing us to move faster. We're in higher gravity, meaning we're under more motion pressure. And that's so the satellite's jiggling a little bit, but it's moving very fast. It has a high velocity. So, and then we're doing the opposite. We're going a slower velocity, 1,000, 20 times slower. Our velocity is 20 times slower, but the amount of up and down jiggling we're doing is 20 times faster.
Window. But in our universe, it doesn't matter how you rotate this atomic clock. The time speed they show is always the same. This is what Michelson-Morley experiment have measured a long time ago.
So we know Michelson-Morley, really buggy kind of ideas about what a photon is, even the whole idea that it needs a medium to transmit it. I mean, that's all crap, and it really doesn't have anything to do with, frankly, again, Einstein's light quanta. The idea of Einstein's light quanta is that you don't have to worry about any medium anymore, that light just moves from one place to another place at the speed of light. It isn't transmitted by a medium.
But the time delay does not depend on the orientation, because you will get the interference on the detector. So in our universe, all clocks behave as if they were stationary the whole time, because these two clocks will always show the same time if they are not moving relative to each other. And if such a pair of clocks were moving relative to them, both of those clocks would be slower by the same rate, but that is only possible due to length contraction of the clock that lies in the direction of motion. Okay, I know I said that when we see other clocks.
So more crap about stuff that's not real. Okay, nothing length contracts by any physical experiment demonstrating it. It's just theory.
Clocks moving, they don't have to show slower time due to longitudinal Doppler effect. The natural question would be, however, can we somehow filter out this effect to measure just pure time dilation? Or in other words, does the Doppler effect in special relativity behave differently than that in a sound wave universe? And the answer is simply yes. In sound wave universe, if you move relative to a certain source, the total Doppler effect would look like this, because you have only the longitudinal effect. In special relativity, the situation is kind of different though, because time dilation is a real fundamental effect and not illusion. If you move...
Says you. Yeah, really. Amazing.
Relative to a certain source, the longitudinal Doppler effect would look like this. And it is simply the combination of the classical longitudinal effect.
So I don't know why he's making it so it's so much more dramatic than the sound, and then you really have to account for the speed you're going. Because frankly, you have to go pretty high speeds to start messing up, Doppler shifting light.
And the transverse effect. But what is the reason for this transverse part if the source wasn't moving in the transverse direction at all? You can analyze the equation for a source moving towards and away from you separately, and you can use Taylor expansion. You see that the first order of beta, there is only a sign difference, as it should be due to classical longitudinal Doppler effect. But when you look at the second order term, you see that the sign is the same. And this is the time dilation contribution. And it is independent on the direction of motion, and it always makes the moving clock run slower. All you need to do now is to create an...
Says you. So again, whatever. There's nothing. They just want to believe.
Experiment that is sensitive enough to measure this second power in beta contribution in the observed frequency. And you are done. Relativity is proven, and it has been done a long time ago. And that's where
Bullshit.
the sound analogy ends. You probably know about the muon paradox.
So this muon thing again. So I did that. I showed the muon experiment, and so it doesn't make much sense how they did the experiment, how you tell the difference between a decay event and an actual muon, because they both do the same thing, which is produce a photon. So,
we detect much higher flux of muons from the upper atmosphere than we should, considering their mean lifetime. The explanation is time dilation.
The explanation is crappy experiments where you really over-exaggerate how capable you are of measuring what you're attempting to measure. And so when you have to make up stuff like, well, let's put 17 layers of bricks because that's how much the atmosphere blocks. It's, a meter of atmosphere is equal to a brick. Well, we didn't prove it. We're just guessing.
But what type of clocks is inside elementary particles? If you still think that time dilation is just a clock issue, then why does it happen to muons?
So again, it doesn't necessarily happen to muons. The experiment's crap. So, it doesn't prove anything. It's got so many fudgeable variables in it that you can make it come out any way you want.
Imagine more fundamental clocks than that inside of elementary particles.
So, and where is the muon in elementary particle? Again, so just why don't you show me that? Why don't you prove to me in some way that it's a decayable entity? that it's what is a muon? I mean, what? We have electrons and protons, and then there's this thing called a muon. What the hell is it? What does it decay into? Oh, it decays into an electron and the magical anti-neutrino. So maybe it's just an electron going fast. Yeah, maybe it's not all that complicated. Maybe it's two electrons going fast.
So there you have it.
It's not decaying like a nucleus decays. It's a whole different process.
Time dilation is about time after all, even though Dialog disagrees. So that is it for this video. And now,
Yeah, it's all about crap. It's all about exaggeration on top of exaggeration, on constant distortion, on top of perversion. Again, the whole thing is dependent on you forcing a photon to have two vectors of velocity, and it can't have two vectors of velocity.
when you fix your view of time dilation, maybe you should also fix length contraction in this video up here. I see you there. Bye.
Yeah, whatever. Let's see if we get anything in response. So we'll see. But yeah, that's just junk physics, frankly. Like I said, likable guy. It's good that he's playing with these subjects. I didn't see anything on electricity not traveling through wires. You think he would have opined on that subject. But anyway, we'll see. But yeah, it's just, physics is just all broken. Like I said, they didn't even get the atom right. They still got the atom with all the swirly bits. Where'd all the momentum come from, and how can the momentum be so precise, the velocities be so precise that they keep everything in, you can't have those precise orbits. You can't have all that precise velocity. It doesn't make any sense. It wouldn't be a stable configuration. And it just makes so much more sense to understand that electrons and protons are held in their charge balance, and they're in real locations, and they're not doing a lot of moving around. They're doing a lot of jiggling, but they're not spinning and whirling and no, just garbage. But anyway, it's all garbage. I got everything wrong. I mean, if every single time they had a choice to make, MV versus MV squared, entanglement versus scatter, every time they had a choice, they picked the silly thing. Every single time. All right. So, enough of video. Till the next time and such. This has been a DraftPhysics.com, DebatePhysics.com video presentation. Yeah, we'll leave the question one more time. So, do you, as a human being, this is what physics says, do you think it takes 100 times the energy to spin a motor 10 times as fast? 10 revolutions per minute takes 100 times more energy than 1 revolution per minute. Yeah. I certainly don't think so. And so I say, if you're going to say it, you ought to show it. That's what you ought to do. If you're going to say it's true, show it's true.